All right, guys. So we ended up with this diagram in the previous video, and it was a schematic of the AA instrument. So we have a light source that points into a flame that flame takes the sample up in, right? And then through the atomizer. And then the light source goes into the monochromator, and the monochromator goes into the detector, and then finally it routes it to the computer or the software unit. Now, this is the schematic of the AA instrument, atomic absorption. And the reason is because it is absorbing light from a light source. Okay? If you do not use the light source at all, and you cut that part out of the machine, what you have now is an AE instrument. All right? So that's a very important difference between the two setups. Every AA can be an AE machine. The only thing that you have to do is make sure that the setting is proper and not use a light source. Because in the AE version, you're just measuring the emission that the light is giving or that the atom is giving off. Okay? So all AAs are AEs because they all can take a light source and they all cannot take or utilize the light source, but you can still measure the wavelengths that are given off through an instrument or through an element. Okay? All right, so that was the schematic that we ended up with. And I said that the very first thing that we're going to talk about is the hollow cathode lamp or the light source. All right. So the light source, if you are part of the course and you've seen other schematics before, the light source is a very common trend in spectroscopy. The light sources very often make all the machines different. For AA and AE, we are typically working in the visible field. All right. If you've paid attention, you've noticed that everything that we've done involves the Roy G. Biv section of the electromagnetic spectrum. What does that mean? Well, all light is composed of multiple parts. Only a small sliver is visible light. That's colored light that you can see. Red, orange, yellow, green, blue, indigo, and violet. All right, so up above the visible, we have typically UV. Down below visible, we typically have infrared. And then microwaves get added on to the mix, and alpha rays and beta rays and gamma rays get added into the mix. We also have radio waves that can be added in. We have a whole assortment of different forms of energy other than colored light. AA and AE is really only going to focus on visible, and that's it. So this is going to be very similar to a UV vis instrument as far as wavelengths are concerned. So with the light source, we're working in the visible portion of the spectrum, and the term that we will be using are wavelengths. Again, if you have already watched the section on ultraviolet visible spectroscopy, this is the same lambda, the same wavelengths that we're talking about with these metals. The light source in the visible region typically goes from 400 to 800 nanometer. Some people will use 900 here instead of 800. It really depends on who you're talking to, but basically, this is the major sector of the visible portion of the spectrum. Of course, we're going to bleed over into the other regions a little bit. For that reason, I'm writing 400 here, but some people would write 390 or 385. So I'm just giving you rounded numbers, and these rounded numbers are really what's used on a daily basis anyway. All right, so visible portion, Roy G. Biv, 400 to 800 nanometers, and we're calling those wavelengths. Again, the wavelength or the abbreviation for wavelength that we use in a laboratory is this kind of triangle looking symbol, and that symbol is lambda, and that lambda represents wavelength. All right? So the first thing that you have to kind of understand is that we don't really call them light bulbs in the atomic absorption and emission world. What we call them is a hollow cathode lamp. And we have an abbreviation for that, of course. That's a capital H, a capital C, and a capital L. A hollow cathode lamp. The HCl do not confuse with hydrochloric acid, please. That would be a lowercase l, not a capital L. Remember those symbol rules back in general chemistry. Those are important. And this is one of those examples. So with the hollowed cathode lamp, I'm just going to kind of draw the typical view or picture of a cathode lamp that you would see. It's basically a rectangular shape with another little piece that kind of pokes out here in the end, and one little piece that pokes out here in the back. Here at the base of the lamp, there's typically a couple of electrodes. We'll talk about these electrodes in just a second. One of those is more of a solid kind of round tunnel, and one of those looks more like a wire. Okay, so this is the hollowed cathode lamp. On the lamp itself, there is a plug-in area. So this is where you would plug the lamp up into the machine. It typically has a couple of prongs that sit out here in the bottom. And then the light energy basically escapes through the front part of the lamp. And this is what goes and hits the atom of interest in the flame. It's okay to touch the lamp. You don't have to be crazy about it. You can handle these with your bare hands. It's all right. These are glass typically that this lamp is made out of. And the only area that we do not want to touch, though, is the tip. All right. So the tip of the lamp is what provides the energy, and we don't want to get this smudgy. We don't want to get this dirty. So we do not want to touch that part of the lamp. But as far as touching the sides and down here at the base, that's perfectly okay. Some people use gloves just to prevent some of the fingerprints and some of the oils from smearing all over the glass. But it's not a necessity, and as long as you keep the glass clean with a chem wipe, you're going to be perfectly okay. All right, so we've got a plug-in area. We have an area up here in the front that provides the energy to the sample. It's okay to touch the lamp with your bare hands, but you don't want to touch the tip of the lamp up here in the very beginning. All right, so the very first thing that you have to pay attention to when it comes to the lamps, it's something pretty important. And there is typically a label down here at the bottom. And this label has some writing on it, and that writing is very important. When that writing is concerned, what happens is that on that label, there will be a number with nanometer that sits after that number, or the symbol for wavelength that sits after that number. That is telling you what the wavelength should be for the machine for your analysis. That number is pretty important. All right. So for instance, I'll pick out a metal that I want to analyze, and then I'll look at the label, and that label is going to tell me what nanometer or what lambda I'm going to have to dial the machine to in order to make the proper measurements. So this is a setting, and that setting is specifically for wavelength. Now, this number, again, goes to the visible spectrum of Roy G. Biv, so we're dialing into a color, basically, is what we're doing, and it's that particular color that that element really enjoys. So we're giving it what it wants. That's the chocolate bar. Something else on the label is going to be something called a slit width. And a slit width you need to think of as a keyhole. So a very narrow slit width. All right, imagine a keyhole in a door. And a narrow slit width is basically going to take a very narrow area and allow the light to see through it. It goes through and out the other end, right? Different colors and different wavelengths behave in a different fashion. That kind of makes sense. You would expect that to happen. And sometimes we have to block out all of the unnecessary light, and we have to put horse blinders onto the machine. And that's the slit width. It's the horse blinder for the instrument, so that way it can do its job and fine tune itself in more detail. A wider slit width would basically take that area and open it up a little more so that the lamp light can go through and out the other end, and there's a wider area that's associated with that slit width. They all will have their own settings. You need to make sure that you take a look at that setting, and you have to make sure that your instrument is going to be finely tuned to that setting. All right? So you've got to dial in the wavelength, and you have to dial in on the slit width. The other piece that's on the label that's pretty important is the recommended voltage. And, sometimes they'll do milliamps. It really depends on the lamp manufacturer. And what you want is you want to make sure that you don't put too much energy into the light bulb. If you put too much energy into the light bulb, too much current, it's going to blow the light bulb and you will not be able to use it anymore. So you have to make sure that you're at the recommended voltage of the lamp. And they're all different because, again, they're all different because they're all reading different metals which behave in a different way. So that voltage you have to dial in on. You have to make sure in the software that it perfectly matches before you use the bulb itself. If not, you're going to blow the bulb, and these hollowed cathode lamps cost a little bit of money, and they are around $1,000 a piece. For the simple ones, they're actually more expensive depending on what kind of metal that you're ordering, and they're more expensive if you buy a lamp that can do more than one metal. We'll get into that a little bit later. So I have to make sure the wavelength is set properly. I have to make sure the slit width is set properly. And I have to make sure that I'm working at the recommended voltage or milliamp. There is a setting on here that says maximum. Over time, the bulb can get dimmer. And maybe it's a little more difficult to do analysis on a dimmer bulb. I should increase the power into it a little bit so it can burn a little bit brighter, so it can do its job a little bit better. So that's why a maximum milliamp is going to be listed on the label. That way you can dial up the power on the lamp a little bit, and you can get it to go a little bit brighter and do its job a little bit better, especially if it's old. However, you never, ever want to go above the maximum milliamp, because that is when you will blow the bulb and you will not be able to use it again, and you've just thrown $1,000 into the trash can. All right? So this is the beginning of the discussion on the hollowed cathode lamp, or HCl, that we will use for the atomic absorption spectrometer. You've got a plug. You'll plug it into the machine. All right? You can handle it with your fingers. That's not a problem. That's okay. You have to make 3 settings on the software, and that's your wavelength, your slit width, and your voltage. And you have to make sure those are set properly before you do any analysis whatsoever.